Welcome everybody to our next video on probability theory. Today we'll be talking about the binomial distribution. Now, the idea of behind the binomial distribution is that it starts with the notion of a Bernoulli trial. A Bernoulli trial is really nothing more than an experiment in which we have two possible outcomes, and of those outcomes we usually call one of them success and the other one failure. So just a little bit of history to go along with that the notion of a Bernoulli trial was really named after the Swiss mathematician Jacob Bernoulli back from the 17th century. So how does this actually fit in, or what really does the binomial distribution tell us? Well, the binomial distribution gives us the probability of a certain number of successes when we have a fixed number of Bernoulli trials. So some examples of where the binomial distribution might pop up. The first one really just being problems on a multiple choice test. So the Bernoulli trial just being success that you get the problem correct, and failure being that you don't get the problem correct. The number of problems on the test then are really just the number of Bernoulli trials that we have going on. So another example might be a batch of items that we get from an assembly line. In that case, success might be that we actually find a defective item. A failure might be that the item is not defective. So somebody in quality control might be interested in, well, how many items can we expect to be defective in a certain batch size? So the number of items in the batch is going to be the number of Bernoulli trials, and the trial just does the part work or does the part not work. So now we get to the question of how exactly is the binomial distribution calculated? Well, something that you can kind of review a little bit is to go back and remember Pascal's triangle and our binomial theorem. So two things that we actually need in calculating the binomial distribution is going to be n, which we call the number of trials that we're doing, and p is going to be the probability of success on any single trial. And so what we have here is the formula for the binomial probability, that the probability of getting k successes is going to be given by n choose k times p to the k times 1 minus p raised to the n minus k power. And then to just kind of talk about what each of those components in that equation have to do, that when we see the p, we remember that's the probability of a success. 1 minus p then is the probability of failure. K is going to be the number of successes that we want to have, and n minus k will then be the number of failures that we have. So let's work an example. Now, suppose we want to roll a fair die, a fair six-sided die, one time. So if we roll a 3, we win. Otherwise, we lose. So let's say that we play the game 8 times. Something that we might ask is, what is the probability that we will win 3 times? So the Bernoulli trial in this case, well, we either win or we lose. Winning is obviously success, and losing is failure. So the probability of success is just going to be 1 out of 6. The only way that we can win is to roll a 3. There's 6 options, so 1 out of 6. And so the flip side of that, the probability of failure is going to be 1 minus the probability of success. So 1 minus 1/6 gives us 5/6 for the probability of failure. The number of trials is the number of times that we're playing the game, 8. The number of successes that we're interested in, k, is 3. So if we look at our formula for the binomial probability, so that's n choose k times p to the k times 1 minus p to the n minus k, then the probability of 3 is going to be 8 choose 3 times 1/6 to the third power times 5/6 raised to the fifth power. We want 3 successes, and so 3 successes means we have 5 failures. So if we expand each one of those, 8 choose 3 gives us 56. 1/6 raised to the third power is 1 over 216. 5/6 raised to the fifth power is 3,125 over 7,776, which, plugging those into the calculator, gives us a decimal that's approximately 0.104190482. So what we can kind of take away from that is that we will win 3 times out of 8 only about 10% of the time. So kind of going along with that, we might reasonably ask ourselves that what is the probability of not winning at all? Is this even a game that we want to play? And so if we look at the probability of 0, that's going to be 8 choose 0 times 1/6 to the 0 power times 5/6 to the 8th power. Well, 8 choose 0 from the calculator is 1. 1/6 to the 0 power, anything non-zero to the 0 power is 1. And if we take 5/6 raised to the 8th power, that gives us 390,625 over 1,679,616, or really a decimal that's approximately 0.232568039. And so what we can take away from that is almost 1/4 of the time that we're playing this game 8 times, we will never ever win at all. So another example of where the binomial theorem pops up is students taking multiple choice tests. So let's say that a student takes a 10-question multiple choice test, and each question has 4 options. Then what we're interested in finding is the probability of the student getting 7 or more questions correct if the student does nothing more than make random guesses. So in this case, the probability of a correct answer is just going to be 1/4. Each question has 4 options. Only one of them is going to be correct, so your probability of success is 1/4. So the flip side of that, the probability of an incorrect answer is going to be 1 minus p, so 1 minus 1/4, or 3/4. Now, the probability of getting 7 questions correct, we just plug 7 into our probability formula. So we've got 10 choose 7 times 1/4 to the 7th power times 3/4 to the 3rd power. 10 choose 7 is going to give us 120. The 1/4 we can make a decimal 0.25, and 3/4 we can make a decimal 0.75. If we plug all of those numbers into the calculator, then we should get something that's approximately 0.0030899905 for the probability of getting 7 questions correct. The probability of getting 8 questions correct, we do the same thing, but now we take 10 choose 8 times 1/4 to the 8th power times 3/4 to the 2nd power. If we want to get 8 questions correct, then we get 2 questions wrong. So if we plug those numbers into the calculator, we get a decimal approximation of 0.000386238. Then if we do the same thing for the probability of getting 9 questions correct, we have 10 choose 9 times 1/4 to the 9th power times 3/4 to the 1st power. Plugging that into the calculator gives us 0.00002861. And if we do the same thing for getting 10 questions correct, so we get 10 choose 10 times 1/4 to the 10th times 3/4 to the 0 power, gives us a decimal approximation of 0.000000954. So the probability of getting all 10 questions correct just by guessing, incredibly small. And so now, if we want to answer our original question, what's the probability of getting 7 or more questions correct? Well, that's going to be the probability of getting 7 correct, plus the probability of 8 correct, plus the probability of 9 correct, plus the probability of 10 correct. And so plugging each one of the numbers that we just calculated in and adding them all together gives us a final probability of 0.003505707. So not even 1% of the time. So really just about 1/3 of 1%, or probably about 3 times for every 1,000 students that take these exams and just guess, will anybody get 7 or more questions correct just by guessing. So hopefully from this video you've kind of seen examples of why the binomial distribution is useful and different areas in which it can be used. Hopefully it's been informative, useful, and I will see you all next time.